In this video, our goal is to use confidence intervals to estimate the population proportion. Remember, everything we learned with confidence intervals, we can do that with an average for the population. We can also do it for a proportion of the population. This video is specifically about proportions. So just to recap from our last video, when we're estimating a proportion, we are going to use a sampling distributions for a sample proportion. But there were some conditions that need to be met in order us to actually use that sampling distribution. Whenever we want to run a confidence interval or construct a confidence interval for a population proportion, we need to make sure that those conditions are still met. So our first condition is that the data is coming from a well-designed random sample or randomized experiment. We need to have randomization. Our second condition is the 10% condition. We need to make sure that there is independence between our selections for our sample. So in order to assume independence, we need to make sure that our sample is no more than 10% of our population. Remember that our sample size is less than 10% of the population. Our sample size needs to be less than 10% of the population. Another condition that needs to happen in order for us to create a confidence interval is the large counts. Remember, the large counts condition helps us assume that our distribution is normal. So in order to make sure that we can construct a confidence interval, we use the same. Our sample size times our probability of success, in this case, our point estimator, p hat, right? What we collect from the sample that we're using, that needs to be greater than or equal to 10. In the same way, we need to have at least 10 failures. N times the probability of failure, or 1 minus p hat, is greater than or equal to 10. In order to assume that our sampling distribution is approximately normal, we need to have these large counts. So remember, there are those three conditions that we need to ensure have been met in order for us to make a confidence interval. So here's an example. Let's assume that we had a bin of beads, red and white, and we took an SRS of 251 beads. Our sample was made up of 107 red and 144 white. What is our point estimate for the unknown proportion of P of red beads in the population? Right? Specifically, we're looking for red beads. So let's answer that question. What is our point estimate? Based off of this one sample of 251 beads, we know that our point estimate is 107 red out of the 251 beads. Let's turn that into a proportion. Let me pull out my calculator. We have 107 divided by 251. We get a proportion of about 42.6%. So now we need to check that the conditions have been met. So let's make sure we can check to see if these conditions have been met. So our first condition, was this a random sample? Yes, we can say yes. An SRS of 251 beads. This meets the random condition. Our second condition, can we assume that we're dealing with less than 10% of the population? Well, it doesn't really say much in our problem. Is N, right, our sample size N is 251, can we assume there are at least 2,510 beads? If we can assume that, then we can continue with our work. If we cannot, we need to stop. For purposes of this problem, let's assume that there are 3,000 beads in the main container. So yes, the 10% condition holds, thus independence. Our third, based off of our point estimate, remember our p hat is 42.6%, so 0.426. I need to make sure I've got at least 10 successes and at least 10 failures, is 251 times that point estimate greater than or equal to 10? Yes. And we can calculate that. We know 251 times 0.426, that gives us the 107. We also need to do that for the probability of failure. So 1 minus that proportion we were talking about earlier for the 251 times 1 minus the 42%. Is that greater than or equal to 10? Well, if we do that, we get 144. So yes, all of our conditions have been met. So how do we actually construct a confidence interval? After we check those conditions, we are allowed to construct our confidence interval. Really quick, here's a recap for a sampling distribution of sample proportions, right? We know that the center of that sampling distribution is the true population proportion. And the standard deviation of that sampling distribution is the equation that follows, the square root of p hat, 1 minus p hat, over n. That's a quick recap. So let's talk about standard error. Standard error, SE, right? We use SE to represent standard error. Because we don't know the value of p, we don't know the true proportion for the population, we're going to replace the sample proportion with p hat. We're going to call this the standard error of the sampling proportion, the standard error, or you can say the standard deviation of the statistic. The standard deviation of the statistic. Since we are constructing the standard deviation based off of a sample that we've collected, we can't say that that's the true standard deviation for the sampling distribution for the sample proportions. So since it's all based off of this statistic that we've just collected, we've given it a new name. So let's pick the correct critical value, right? Take a quick recap. If we're talking about a confidence interval, remember the confidence interval is known as the point estimator plus or minus the margin of error. The point estimator here specifically being p hat plus or minus. If you remember at the end of our last video, the margin of error was defined as a critical value times the standard deviation of the statistic. So we just covered the standard deviation of the statistic, right? It's basically a standard deviation based off of the point estimator that we've calculated or collected. Now we need to talk about the critical value. Remember, the critical value is how many standard deviations are we looking for? So how do we select that correct critical value? We can get more precise values from a calculator or a table, but if we check the central 95, we can see that it's marked by a z-score of 196. Now, you remember before the empirical rule, 68, 95, and 99.7, all relating to 1 standard deviation, 2 standard deviations, and 3 standard deviations. Well, that wasn't exactly correct. 2 standard deviations is not actually 95%. When we look mathematically, 1.96 standard deviations is the true 95% that will be under our curve. So we're no longer going to think of 2 standard deviations for the 95%. It's really important that we think of 1.96. This value, where is it coming from? It's coming from a table of values that you would find at the back of any statistics book. If you wanted to actually calculate the area under a normal distribution, this is something that we're just going to take for face value right now. When we're talking about a z-score of 1.96 standard deviations, that's telling us we're going to have 95% of the area under the curve. Between negative 1.96 and positive 1.96 standard deviations. So the fact that I have an asterisk here, this little asterisk, all that is saying that this is talking about a critical value, not necessarily a z-score. So we want to use technology. We're just going to use technology to find the critical value z for an 80% confidence interval, assuming that the large counts condition is met. Before we go to our calculators, let's just take a second to think about this. If I have a normal distribution and I want 80%, that means I have an area of 0.8 in the center of my normal distribution. Well, think about it. If I have 100% and I'm subtracting 80%, that means I'm left with 20%. That 20% technically needs to be divided into 2 equal parts because there are 2 equal areas under my curve that will share that 20%. That's telling me that I have 10% on either side of my center, 80% in my normal model. Now, in order to find that z-score, there are different things we can do. We can use a table, or what most of us will use, if you remember, is the inverse normal function on our calculator. And we're going to plug in, there's 2 things we could do. We could plug in 10%. We can do the inverse 10% of our area. That's going to give us some value. We could also use the inverse norm of 90%. The inverse 10 or the inverse 90 will still give us the same critical value. The only difference is one will be negative and one will be positive. So just like before in your calculators, go ahead and go to math. I go to statistics, distributions, and inverse norm with an area of and your choice. You're going to get 1.28. Right, so that's saying if I want to construct a confidence interval that has a level of confidence of 80%, the critical value that I'm going to use is 1.28. So let's get an actual formula. For a 1 sample z interval for a population proportion, we need to make sure all the conditions are met. The level of confidence is going to affect our critical value. And this is our equation, the point estimate plus or minus the margin of error. Remember, all of this is the margin of error. The margin of error is broken up into 2 parts, the critical value and the standard error of the statistic, the standard deviation of the statistic. So let's do that example from earlier. So we took an SRS of beads from the container and got 107 red beads and 144 white beads. Calculate and interpret a 90% confidence interval for the true population parameter, the true population proportion. So let's start there. We know that p hat here from earlier, p hat was the 107 beads over the 251 total, giving us 42.6%. That's our point estimate. And we need to interpret a 90% confidence interval. We've already checked the conditions. We don't need to do that. Let's just go straight into calculating our interval. Now, we need a 90% confidence interval. So let's take a second to think about that. If I have a normal distribution with a center 90%, that leaves me with 10% left over to evenly distribute on either tail, telling me that I need to know the inverse norm of 5%, or I can do the inverse norm of 95%. All right, I can do the inverse norm of 95%. Either way, these are going to give me the same value. One will be positive, one will be negative. Doing that in my calculator, I'm going to find out my critical value is 1.645. Now I want to construct my confidence interval, right? I need to use the standard deviation of the statistic, right? We know the SE, standard error, is equal to the square root of 0.426 times 1 minus that, all divided by my sample size of 251. And we'll plug that into the calculator later. So putting this all together, I've got 0.426 plus or minus 1.645 times the square root of 0.426 times 1 minus 4.26, or 0.426, I'm sorry, divided by 251. This gives me 0.426 plus or minus 0.051, telling me that my confidence interval is 37.5% to 47.7%. So how would I interpret this? I can say we are 90% confident that the interval of 37.5% to 47.7% contains the true proportion of red beads. 90% confident that the interval, running out of space there, of what we solved for contains the true proportion of red beads. Now to look at B is asking us, B was saying, Mr. H claims that exactly half of the beads in the container are red. Let's use this confidence interval. Half the beads, 50%. Does 50% lie in our interval? It does not. So I could say, for B at least, based on our confidence interval, we can reject Mr. H's claim. And that's it. That's our entire work. So whenever we're working with confidence intervals, it's really important that we follow this 4-step process. State the parameter that we want to estimate and what confidence level we are doing. Plan, we need to identify the appropriate inference methods. We need to check all of our conditions. And lastly, we need to do the actual calculations given that the conditions have been met. Lastly, we need to conclude. This 4-step process is the way to receive full credit on your AP exam. So let's go ahead and do this other example. The Gallup Youth Survey asked a random sample of 439 people, 439 US teens aged 13 to 17, whether they thought young people should wait to have sex until marriage. Of the sample, 246 said yes. We need to construct and interpret a 95% confidence interval for the proportion of all teens who would say yes if asked this question. So let's go through that 4-step process. What do we want? What are we stating? We want to estimate if, or we want to estimate the true proportion P of all teens 13 to 17 that say they should wait. For marriage, to have sex. So what are we doing? We're going to construct a 95% interval. 95% confidence interval. Next, let's plan. In the plan state, we need to make sure that all of our conditions are met. Random. Because of an SRS of 439 teens, yes, we can say that the random condition has been met. As far as the 10% condition, the 10% condition tells us independence. The sample size, 439 times 10 equals 4,390. We can assume more than 4,390 teens exist. And then let's check our large counts. For our large counts, we have 439 times P. What is P? Well, we need to check our actual proportion that's here in our problem, right? We know that there are 246 out of the 439. Let me plug that into our calculator. We're given a proportion of 56%. So with a sample size of 439, with half of them being a probability of success, we can assume, yes, that is going to be greater than or equal to 10. The same with the failure, 439 times 1 minus the 56%. That will also be greater than or equal to 10. So we've checked our 3 conditions, and all 3 have been met. Now that we've checked our conditions, we can actually do our problem. So remember, in order to run this, we have the point estimator plus or minus the critical value times the standard error divided by our sample size. So our point estimator, which we know was 56%, plus or minus, we need to select the appropriate critical value for a 95% confidence interval. Now, if you remember from earlier, I said that new 95% confidence interval is 1.96. It's no longer 2, right? The empirical rule doesn't follow us anymore. That was just for the beginning of stats. We're looking at 1.96 times our point estimate, 56, times the opposite of that, which is 44, all divided by our sample size of 439. With this here, we do some of the math. We get 56 plus or minus 4.6%, giving us the confidence interval of 51.4% to 60.6%. We found our confidence interval. Now we need to conclude, right? We need to put some words to that. So we are 95% confident that the true, or the population proportion of teens waiting, or teens that say yes to wait for marriage before sex is between 51.4% and 60.6%. Make sure that you do all 4 of these steps: state, plan, do, conclude. So how do we use our calculators in order to do this? Let me go ahead and show you. So for those of you on the Nspire, let's go ahead and open up the Nspire. I take that back. It looks like we're doing the 84 first. For those with the 84, go ahead and go to Statistic, which is right here. Click on Stat. I need you to go over to the column that says Tests. Under Tests, I need you to go all the way down until you see the 1 proportion Z interval, right? We're dealing with proportions. This is 1 proportion. It's labeled as A. Go ahead and open that. You can plug in the information that you have, right? Based off of the sample that you've collected, we know that there are 246 in our sample out of a sample size of 439. You're not plugging in the percentage, you're plugging in your actual observations. We want that 95% confidence interval, and we'll hit calculate. And the information will show up for us right here. For those of us that want to do the Nspire, in a home screen, dealing from a home screen, right? I need you to hit Menu. I need you to go down to Statistics. From here in Statistics, if you go down to number 6, it says confidence interval. Same option, the 1 proportion Z interval, 1 proportion Z interval. The number of successes, right, 246. Our sample size is 439, 95% confident. Click OK. It tells us our lower bound, our upper bound. It even asks us for, or it even tells us our sample statistic, and it tells us the margin of error. Remember, the margin of error is plus or minus the sample statistic to give us our upper and lower bounds. So as we work with confidence intervals, there's one more skill that's really important for us to know how to do is how do we choose the correct sample size? We often want to choose a sample size that allows us to estimate a population proportion within a given margin of error, right? Remember, the margin of error is that last part of our confidence interval. It's the plus or minus the margin of error. The margin of error, if you don't remember, is defined as the critical value times the standard error or the standard deviation of the statistic, right? So since the margin of error involves p hat, we have to guess when choosing n, right? Use a guess for p hat based on a pilot study or on a past experience with similar studies, right? Assuming that we haven't actually collected data yet, we need to guess based off of what's happened before us. If you want to make sure that you are selecting a large enough sample size, always assume that you want to use a proportion of 50%. The margin of error is the largest when the statistic is 50%. So guessing 50% is going to make sure that we at least cover the values of what we need. If you don't know, when in doubt, always use 50% as your sample statistic. So to determine the sample size that will yield a C percent level of confidence for a population proportion with a margin of error, solve this inequality, right? We have our critical value. This will be based off of what we're looking for, a 90%, a 95%, an 80% confidence interval, right? For here, use 50%. If you don't know anything based off of previous studies, it's safe to use 50%. Solve for the margin of error that you're looking for. This will often be given to you because ultimately we're trying to solve for the sample size. Read your problem and see what it says. So let's go through this one example. A company has received complaints about its customer service. The managers intend to hire a consultant to carry out a survey of customers. Before contacting the consultant, the company president wants some idea of the sample size that she will be required to pay for. One critical question is the degree of satisfaction with the company's customer service measured on a 5-point scale. The president wants to estimate the proportion P of customers who are satisfied, that is, who choose either somewhat satisfied or very satisfied. The two highest levels on the 5-point scale. She decides that she wants to have the estimate be within 3% at a 95% confidence level. How large of a sample is needed? So our problem is to determine the sample size needed to estimate a proportion within a 3% margin of error with a 95% level of confidence. Well, remember, our critical value times our standard error, we need that to be less than or equal to the margin of error that we're looking for. We know that the margin of error, she wants it to be no more than 3%, and we want a confidence level of 95%. To have that confidence level of 95%, hopefully by now we've associated a critical value of 1.96 times, remember, we want to assume 50%. This is going to be the most conservative sample statistic we can estimate. So 50% times 1 minus 50% over a sample size of n. We're trying to solve for n, and this needs to be less than or equal to 3%. So we can go ahead and start to do the math. Let's see what we get. Let's start by dividing both sides by 1.96. We're going to get the square root of, I'm going to simplify that inside, 50% squared over n is less than or equal to from here I can square both sides. We get 0.5 squared over n less than or equal to from here doing some math and manipulation, we're going to get, let's see, 0.5 squared technically I can swap the place of these two, right? I can divide and multiply by both sides. Ultimately, in the end, I'm going to get 0.25 over 0.003457. That's less than or equal to n. Doing that math and making sure that we have the actual answer, I know my sample size needs to be greater than or equal to 1067.11, right? So in order to actually make sure that I have a margin of error that's no more than 3%, I need a sample size of at least 1,068 people.